Today we were going to be resolving this question. It asks us to use the force and point at B is fixed. So we know if pins, they have two reactions, horizontal and vertical. Horizontal and vertical. For fix here, we have horizontal, a vertical, and a moment. So first things first, you have to know the degree of determinacy. So we use this formula. Okay, so if this is equal with this is determinate, but if it's not, that means if it's indeterminate. So the R stands for reaction. So here we have 1, 2, 3, 4, 5, 6, 7. So 3 times N is the beam that connects these two. So 7 is bigger than 6, so this means that our structure is indeterminate to the first degree. Alright, so first things first that you want to do is you want to draw the principle of superposition. Okay, so to draw that, you'll have three things: actual frame, primary structure, and redundant applied. So we will first draw the actual frame. So the actual free body diagram of the actual frame looks like this. So we have a 3 meters here. We have a 6 meters here. So this is A, B, and C. So I'm just gonna use the blue pen to draw the reactions. So this is AX and AY. Pins have two reactions. Same with CY, and CX. Okay, so this is a distributed load between A and B. It says 60 kilonewton per meter. B and C, you got 30 kilonewton per meter. Alright, so this is called the actual frame. Okay, so next you want to draw the primary structure. The primary structure shows that you are taking away one extra reaction. In this case, I'm gonna turn this C pin into a roller. So a roller only has one reaction, which is a vertical reaction. So then our structure will be determinate. So we were taking one because it is indeterminate to the first degree. So let's draw the free body diagram again. Okay, so I'm changing this to a roller, right? So let me just A, B, and C. A roller has only vertical reaction. So here we have, as usual, AX and AY. So here we're gonna put 30 kilonewton per meter. Over here we have 60 kilonewton per meter. And then we're gonna draw the deflection curve in this structure. So over here it has a distributed load like this, so it deflects like this, and over here it deflects like this. Since we don't have a horizontal force here, so that's why it goes like this. So we call this little distance right here, we call this delta C. Alright, so this is called primary structure. Okay, and then we're gonna draw another free body diagram, and we are gonna reapply the redundant that we take away here. So we took away CX, right? So we're gonna apply it again here. So I'm just A, B, and C. we have Cx here. We apply it again. So let's draw the deflection curve now that is reapplied. So this one is still like this. So since we apply it over here, so it goes like this in this direction. So from this distance over here to this distance, it is called force X times unit load of this force right here. So this is redundant Cx reapplied. So as you can see here, the actual frame is actually the summation of primary structure and redundant applied. So this one cancels this one, so that's why we have this. All right, so next we are gonna write the compatibility equation. All right, so we're gonna find out the compatibility equation. So like I said, over here we have zero reaction here. No, so equals to this one, primary structure, we took away the redundant Cx and we replace this with delta C. Okay, and we're gonna add the redundant Cx applied. So Cx and times the unit load. Okay, so here we can see that this is actually a negative because this goes in this direction. So this is negative, this is positive. So hence is why the negative delta C. Alright, after that we are gonna draw the primary structure again. Okay, we'll just draw this one over here. So it looks like this. A, B, and C. We got AX. We got AY, and this is only CY because we took away the redundant and the primary structure. So we still have the distributed load over here. And over here. So first things first, we want to find the value of CY and AY. Alright? So we are going to find it by using the moment, total moment from the point A. So we got 60 and 3. We got this one 1.5 plus CY and 6. Okay, so then we solve this and then we will get CY equals to 202.5 kilonewton. Okay, and then we want to find AY. We use a summation of force in the y direction. So 202.5 minus 60 times 6 and then plus AY equals to 0. So solving this, we got AY equals to 157.5 kilonewton. Okay, so next, after we found this, we are going to separate this into few sections. So we're gonna take this section right here, and then we're gonna cut this section right here. So I will call this 1, 1. This is 1, 2, 2. Okay. So let's solve the case 1, 1 first. This one. So let's draw the free body diagram of this. We have, this is A. We have a AY, which is 157.5, and then we got a distributed load here 60, and then this is a distance x1. Then we get a moment here. Okay, so then we're gonna find the total moment from this point right here, equals to 0. So this is negative 157.5, because this is clockwise, times x1 plus 60 times x1 and x0 plus m1 right here equals to 0. So 60 times x, and then we take the middle here. So this is a concentrated force right here, and then we take it in the middle. So hence is x divided by 2. So solving this in terms of m1, we got negative 30x 1 square plus 157.5 x1. Okay, so next we're gonna solve for the case 2, 2. So this area. So let's just draw the free body diagram of that. We have C here, and we get a CY, which is 202.5 kilonewton, and then we get a distributed load here 30, and then we get a x2 distance, and then we get a moment. Don't forget the moment, m2. So we'll just assume this right here. So we're gonna do the same thing we do over here, and then we're gonna find the total of moments from this point. Okay, so we got this is clockwise, so it's negative, and then this clockwise also, so it's negative 30 x2, and we make it a concentrated force, and then we times by the distance from here to here. So this is x, and then we find half of it. So solving in terms of m2, we got negative 15 x2 square. Okay, so next